Okay, welcome back, everybody. I think that there are 3 more weeks of class. 9 lectures. The last week of class, there will be a second midterm. I've been told I can't call it a final. It's a midterm 2.0. And it looks like we're actually going to finish everything I wanted to tell you, which is kind of amazing. So this week, I'm going to tell you about Laplace transforms, which are essentially a more powerful generalization of Fourier transforms for slightly badly behaved functions. Okay? Fourier transforms are a really good thought experiment and a really good coordinate system to write functions in, but Laplace transforms are perhaps a bit more powerful for everyday solving of equations by hand. Okay, so today I'm going to tell you what the Laplace transform is and why we need it. And then in the next 2 lectures, I'm going to tell you how we use these to solve ordinary differential equations and partial differential equations. Okay? And how many of you have seen Laplace transforms before? Okay, how many of you have seen them used to solve ODEs, like the harmonic oscillator? Okay, what about in control systems, maybe? A little bit? Okay, so this is going to be a review for maybe about 1/3 to 1/2 of you, but that's okay. We're going to go a little bit more in depth, and we're going to make connections to the Fourier transform and also make connections between ODEs and PDEs. So I apologize if things kind of jump back and forth a little bit. This entire week is going to be Laplace transforms. We will do a little bit in MATLAB, kind of how MATLAB deals with Laplace transforms. And then in the last 2 weeks, we're going to get back to data and numerics, things like that. Okay, any questions at all about anything right now? Questions about the organization, what we're learning, why we're learning it, big picture, anything? I think this is a short lecture. Okay, maybe I'll just jump in. So the Fourier transform allowed us to generalize Fourier series to what types of functions? Well, so Fourier series were defined for periodic functions, and we allowed these to generalize to non-periodic functions over the entire real axis, from -infinity to infinity. Okay, so the Fourier transform. Okay, let's try one more time. Shit. All right. So the Fourier transform is defined on the entire real axis from -infinity to infinity. Let's say from x in -infinity to infinity. And it's also defined for well-behaved functions. And what do I mean by a well-behaved function in this context? So it actually doesn't have to be continuous. My function can be discontinuous, and I can still do the Fourier transform, like I can do the square wave. It's not perfect, but in the limit, then my Fourier transform is fine. What other types of functions are well behaved? What are the other properties of f that make it so I can do a Fourier transform? So it doesn't have to be smooth, doesn't have to be continuous, but it has to be, it can only have countably many discontinuities, meaning it can only have, like, I should be able to count the number of discontinuities. They should be ordered in some way. What is the kind of main property of the Fourier transform function f? Not periodic. Doesn't have to be periodic. It has to taper off to 0 at infinity, right? It has to be a bounded L1 function, meaning it doesn't blow up as x goes to infinity. So the magnitude, so my function f of x has to go to 0 as the magnitude of x goes to infinity. So this is bounded asymptotically. Actually, more than bounded, it converges to 0. Bounded asymptotically to 0. And that just is a way of saying that our function tapers off to 0 as x goes to plus or minus infinity. But lots of functions that we're interested in don't do this. Like, what are some example functions that we see all the time that don't have this property? Sine. Sorry? Ramp function or a Heaviside function. So the Heaviside is a good one. So it's not heavy like this is a heavy rock. It's Heaviside, like the person who invented it was named Heaviside. It's a very convenient name because his function looks like a Heaviside function starting at 0. So it's 0 everywhere. So if I wanted to write this formally, I would say h of x equals 0 for x less than 0, 1 for x greater than 0, and I don't really care what happens exactly at x equals 0. So I'm not going to include it. So this is a function that we use all the time in control theory, and I'll show you why this is useful later. A ramp function would also be an example. What are some other functions that are not bounded and not well behaved? Maybe even blow up. Exponentials are good. Cosine sines, exponentials, Heavisides, ramps, all kinds of functions. Polynomials, x squared, right? X cubed, x to the 4th. These are all functions we want to be able to work with. Fourier transforms can't handle them. Okay? So I'm in a bad pen situation here. So what's a possible solution? What if I want to Fourier transform these functions, but they're going to blow up? They blow up as x goes to plus and minus infinity. What's a possible way I can fix this? I could take derivatives, but oftentimes if my function blows up, then the derivatives also blow up, so exponentials will blow up. This Heaviside derivative will be pretty well behaved, except it'll have a delta function at 0. I can Fourier transform a delta function, no problem. What are some other ideas? What could I do to these functions to make them better behaved so I can take the Fourier transform? What's the fundamental problem we're having? They're not converging. They're not going to 0. How do I make a function go to 0 at plus and minus? Sorry?
1 by fx.
Well, I don't want to divide 1 by fx because then it might blow up at the origin or it might blow up somewhere else. That's kind of a dangerous way to try to make this converge.
Bounded by a function we know that is convergent.
Yeah, so maybe I'll multiply it by a really, really strongly decaying function. I'll kind of regularize this down to 0. So the solution, that's exactly right. So the solution would be to multiply our badly behaved function let's call this, I'm going to switch to time. In Fourier domain, I usually have functions of x. In Laplace domain, I usually think of them as functions of time for reasons you'll see very, very shortly. So I take my badly behaved function of time and multiply by strongly damped or strongly decaying function. And that strongly decaying function is going to look like e to the minus gamma t. So I have some new function, big F of t, equals e to the minus gamma t times my original badly behaved function f of t. And I'm going to choose this gamma large enough that this is forced to decay for time going to positive infinity. Okay? And then I'm going to Fourier transform big F. So I want to be doing this Fourier transform. I still think that Fourier transforms are going to be a useful concept, but I can't do Fourier transforms on my badly behaved function. So I multiply them by a really largely damped exponential, and then I can Fourier transform this. Okay, so and what we're going to do is we're only going to consider positive time. So t greater than 0. There's a couple of reasons for this. The first reason is if my badly behaved function is badly behaved in both negative and positive infinity, then there's no function, I can't multiply it by this function and make it decay on either side. Okay, so if I want to multiply this by a simple exponential decay function, then this is only going to decay for time going to positive infinity. If I wanted to multiply this by a function that would decay in negative and positive infinity, what would I do? I'd multiply it by a Gaussian, right? I'd multiply it by e to the minus gamma t squared, a Gaussian. That would be fine. And you could very well define a two-sided regularizing, something like a Laplace transform, but for plus and minus infinity. You could totally do that. I'm sure this has a name. I don't know what it's called. But there's a lot of these named transforms. But I'm switching to variable time because we usually care about what's happening after now. I don't care about what happened in the past. I start now, and I care about things converging to positive infinity. So we can do this trick of multiplying by a decaying function, and we're only going to consider positive time. So Laplace transforms we usually think of as referring to time. They could refer to space, and we'll do that later. Okay, so our function f of t is really equal to 0 for time less than 0, and it's equal to this thing, e to the minus gamma t, f of t, for t greater than 0. Okay, and there's a couple of assumptions we're making. So we assume, and these are pretty reasonable assumptions, I think you'll agree. So we assume that our function f of t is always bounded by some constant e to the alpha t for some k and some alpha. Alpha could be positive. It could be 1,000 or 1,000,000. It could be a hugely fastly growing exponential. But we're assuming that f is bounded by some exponential, which most functions we care about are. Try to think of a really nasty function that's not bounded by an exponential. We don't have a lot of them in our arsenal. Most functions we care about are at least bounded by an exponential. Okay? So we assume that f, our function, is badly behaved, but it's not arbitrarily badly behaved. It at least is bounded by some exponential growth. And we choose gamma to be larger than alpha. So we choose our decay. So basically, we choose our damping. Gamma is larger than the growth alpha. Okay? So this is just a kind of mathematically precise way of guaranteeing that this function f of t is going to converge like I want it to, meaning that I can do the Fourier transform. Does this make sense? Okay, we want to be able to generalize Fourier transforms to badly behaved functions. We do it this way. Lots of other ways you could do it, but this is particularly nice because doing integrals with exponentials is particularly easy. I don't want to do Gaussians because they're a pain. I don't want to do some other function because they're also a pain. This is the easiest function I can multiply by and make this well behaved. Okay, if there's any questions, please interrupt at any time. Okay, so the next part is simple. We're going to Fourier transform this new function, big F of t, and we're going to see how that relates to our little function, little f of t. So I'm saying that this is generally true for functions of time, t greater than 0, but you could also imagine that I could have this infinitely long, thin piece of metal, this rod, except it's only half of infinity. It starts at x equals 0, and it goes to that direction to positive infinity, but it doesn't go in that direction to positive infinity. So I could also think of Laplace transforms over some finite region, some infinite but half infinite region of space. And we'll do that later on Friday. Doesn't matter what the variable is. It's just time makes a lot of sense. Okay, so now what we're going to do is we're going to Fourier transform this big function f, and we're going to essentially derive the Laplace transform from the Fourier transform of this big function f. Okay, so Fourier transform of f of t equals e to the minus gamma t f little f of t. Okay, so what's my Fourier transform? Big F hat of omega equals. You guys should know this by heart now. This should be something, if you wake up in the middle of the night, you should be able to recite this when you're groggy. Come on. I know there's an integral. Okay, it goes from negative infinity to infinity of e to the minus I omega t times this whole thing, e to the minus gamma t f of t dt. Did I mess that up, or is that right? Seems right. Okay, good. And because this function f is only defined on positive t, everything, minus infinity to 0 is equal to 0. Okay, so I'm just going to say that this is equal to the integral 0 to infinity of, I'm going to use shorthand here. This is really f of t e to the I omega t dt. And what about the inverse Fourier transform? F of t equals 1 over 2 pi. Integral, now this really is an integral from minus infinity to infinity because my frequency omega can still be defined on all positive and negative frequencies. Of f hat omega e to the positive I omega t d omega. And the last thing, I'm just writing down the Fourier transform in terms of f. This is totally review. We know what this is. But now I'm going to take this f hat, and I'm going to replace it by this expression here. So I'm going to get 1 over 2 pi times the integral minus infinity to infinity of e to the I omega t integral 0 to infinity of f of tau e to the minus I omega tau d tau on this integral, d omega on this integral. Okay. Yes. Okay, good. Okay, so what I really want to do is I want to find a transform in terms of my original function, little f. So everywhere I see a big F, I'm going to replace it with e to the minus gamma t little f of t. Okay? And what I'm essentially going to do is I'm going to try to find something like, so notice that f of t equals some nasty double transform of f of t. This is basically saying that if I Fourier transform f, and then I inverse Fourier transform f, I get back f. And I want to find a similar pair, a similar Fourier inverse Fourier transform pair for little f. So that's where we're going. This is a little bit long-winded, but I want to tell you where we're going. Okay, so I notice that this is e to the minus gamma t little f of t. And that equals 1 over 2 pi integral minus infinity to infinity of this thing, e to the I omega t integral 0 to infinity of f of t times e to the minus gamma t times e to the minus I omega t is e to the minus gamma plus I omega, these should be taus, d tau d omega. Okay, we're almost there, super close. So the last thing we want to do now we have some, f of t equals some transform of a transform of f. This is getting very close to what we want, except we need to get rid of this exponential on both sides. So I'm going to multiply both sides by e to the positive gamma t times e to the positive gamma t. So I'm going to get my function of time is equal to 1 over 2 pi integral minus infinity to infinity e to the gamma plus I omega t, because I multiplied both sides by e to the gamma t, times the integral 0 to infinity f of tau e to the minus gamma plus I omega tau d omega. Okay, good. So this is looking strikingly like a Fourier transform pair, except instead of e to the I omega t, I have e to the gamma plus I omega t. Okay, so I omega has been replaced by gamma plus I omega. Oh, I should put this down. Okay, the last step is actually kind of breaking this up into two transforms, a forward Laplace transform and an inverse Laplace transform. Okay, so what we're going to do is we're essentially going to give this gamma plus I omega a dummy variable. We're going to say let S equal gamma plus I omega be our Laplace variable. And essentially this is a generalized frequency. And we'll talk about what that means to be a generalized frequency in just a minute. It's pretty simple. So what is ds? If I took the differential ds, what would ds equal? D gamma plus I d omega, but gamma is a constant. D gamma is 0, so this is just I d omega, which means that d omega, my differential in omega, is equal to ds over I. Okay, so everywhere in that integral where I see a d omega, I'm going to just swap it out with a ds divided by I. So the last thing we have is f of time equals 1 over 2 pi, and I'm going to pop this, I'm going to convert this to ds over I, and I'm going to take the I out. So this is 1 over 2 pi I integral. Now instead of d omega, I'm integrating with respect to ds. So if I was integrating from omega equals minus infinity to infinity, then s is going from gamma minus I infinity to gamma plus I infinity. My s variable is gamma plus I omega. Gamma plus I omega, and omega was going from minus infinity to plus infinity. So this is an integral from gamma minus I infinity to gamma plus I infinity of e to the st. Remember that's gamma plus I omega is just s. Times the integral from 0 to infinity of f of tau e to the minus s tau d tau ds. Okay, we're super close now. This is almost exactly like the Fourier transform pair. And now I can actually split this up. I can say, okay, my Laplace transform variable, I'm going to call it, instead of a hat for Fourier, I'm giving it a flat bar hat. And instead of being a function of omega, it's a function of s, which is gamma plus I omega. So this Laplace transform, this is the Laplace transform of my function of t. And it's just equal to this integral here. So integral 0 to infinity of f of t e to the minus st dt. Good. And my inverse Laplace transform, so if I want to get my function of time back, I take the inverse Laplace transform of f bar, and that equals 1 over 2 pi I, integral from gamma minus I infinity to gamma plus I infinity of f bar of s e to the positive st ds. That's a shame that I don't have a red pen, because this would have big red stars, because this is extremely important. Okay? So the Laplace transform is just a Fourier transform of my function times an exponential decay. That's all it is. And if I go through those steps on the left, reconfiguring this thing, I can find these new functions, this simplification, this is like just simplifying my expression. I get this new expression f bar of a new frequency variable s is equal to this function. And this is its inverse Laplace transform. Okay, this is a good place to stop and wait for questions. Yeah?
Could you kind of recap
Yeah.
exactly what we're through?
Good. Okay. We want to Fourier transform a function f, but it's badly behaved. So first we multiply it by an exponential decay, and then we Fourier transform it. And in the process of Fourier transforming our decayed kind of nice function big F, I essentially try to write it. I try to write big F equals inverse Fourier transform of Fourier transform of F. So I want a pair of Fourier transform and inverse Fourier transform. And then I plug in my exponential decay everywhere I see my F. And I simplify, simplify, simplify until I get something that's like my original function times some inverse transform times some transform of F. And this transform looks remarkably like the Fourier transform, but it's a little different. Instead of integrating from I minus I infinity to I infinity, I'm integrating from gamma plus I minus I infinity to gamma plus I infinity. So it's basically a Fourier transform, except I'm integrating on a different contour. And I should draw that picture. Okay, so originally, so for my inverse Fourier transform, this is in the complex plane. I have minus I infinity and I infinity up here. So normally what I do for the Fourier transform is I'd have something like 1 over 2 pi integral minus infinity to infinity of e to the I omega t f of t. So I would integrate from here all the way up here. And that's how I would get my inverse Fourier transform. But now because my function f might be unstable, I have to multiply it by some e to the minus gamma t. And so my inverse Laplace transform contour integral is along this curve from gamma minus I infinity up to gamma plus I infinity, where gamma is larger than the largest growth of f. So I have to do this integral here. And remember when we did complex analysis, we actually know how to compute this integral because maybe our function, maybe this function here has some poles, some, divided by s minus a's, maybe it has some poles. Maybe it's even unstable. But I can still take this contour integral and essentially compute this large closed integral. I can use the Cauchy integral formula and the ML bound to prove that this part has to be 0. And I can get an expression for what this integral equals in terms of the sum of all of the Cauchy integral formula terms. Would it help if I wrote down what the Fourier transform pair was? Yes? I think so. Okay. Because I really want to convince you that this Laplace transform it really is the Fourier transform on my function if I multiplied it by e to the minus gamma t. That's exactly what I did. I Fourier transformed my function times e to the minus gamma t. So let's say, and what I want to get at is if my function is well behaved, then this actually turns exactly back into the Fourier transform, or almost exactly, except it's on 0 to infinity instead of minus infinity to infinity. So what would my normal Fourier transform look like? So that would be f hat of omega equals integral from minus infinity to infinity of f of t e to the minus I omega t dt. And the inverse Fourier transform f of t, if I want to get that back, it's 1 over 2 pi integral minus infinity to infinity of my Fourier transformed f hat times e to the plus I omega t d omega. So let's say that my function f down here is actually well behaved. It is bounded at plus and minus infinity, and I don't have to multiply it by any decay. So gamma is 0. I just multiply it by 1, e to the 0 of t. Okay, so let's say that now we have s equals gamma plus I omega, but gamma is 0. So that's just equals I omega. So here I'm integrating, anytime you see an s, plug in an I omega, right? So this is e to the minus I omega t. And I'm integrating from 0 to infinity because f is equal to 0 for negative times. So this is actually equal to minus infinity to infinity of f of t e to the minus st dt if f of t is equal to 0 for negative time. Right? If this function is 0 for negative time, then I can make this a negative infinity to infinity. And this looks exactly like the Fourier transform if my function was already well behaved. Now, how about the inverse Fourier transform part? Okay, so remember our ds equals 1 over I d omega. No, that's not right. ds equals I d omega. So my i's cancel. And if my function was well behaved, then gamma is 0. And so this is just the integral from minus I infinity to I infinity. So minus infinity to infinity. And instead of an s here, I would have an I omega. And here I have an I omega. These are identical transforms if my function f is well behaved and is equal to 0 for negative time. Identical. So the Laplace transform is purely a generalization of the Fourier transform for functions that are not well behaved, where I do have to multiply by a real damping, and where my function is definitely only defined for positive time. And you can think of it basically like doing the Fourier transform of that new function that has been made to decay. Okay, other questions about this? Yeah.
What can't the Laplace transform other than positive negative terms?
It can't transform things that grow faster than exponential. Any examples anyone can give me of things that grow faster than exponentials? X to the what?
X to some large.
X to some large power is actually smaller than exponential growth. If you took the log of it, it would be, it basically is exponential growth, but in a different base.
Anything with the vertical asymptote?
Sorry?
Anything with the vertical asymptote?
Anything with a vertical asymptote. So if I had like y dot equals minus y squared, this will blow up to infinity in finite time. I think. Not this. This is a bad one. There are ODEs whose solutions blow up to infinity in finite time, and the solutions would definitely not work. Another example is the factorial function. Okay, so if I had like maybe like f of t equals t factorial. So this is only defined on integers, right? But if I had, does everyone know the factorial function? Like 5 factorial is 5 times 4 times 3 times 2 times 1, so it's huge. 10 factorial is way bigger. 1,000,000 factorial is astronomically large. Factorial grows faster than almost anything else. And there's a generalization of factorial called the gamma function. So it extends factorial to real valued numbers. So you can have, but basically gamma is way, way, way worse than exponential. It's like a factorial in F. So the Laplace transform doesn't work for everything, but it works for most things that we're comfortable with. Power functions, exponential functions, even really, really nasty exponential functions are fine. I think if I had e to the t squared, would that work? I don't think so, but I don't know for sure. I don't think it would work. But you could make another generalized Laplace transform where instead of multiplying it by e to the minus gamma t, you multiplied it by that Gaussian we talked about. You could do an even more generalized transform. That would be totally fine. Yeah.
Is the ease of computation really reason why they multiplied it by an exponential and called it a Laplace transform instead of multiplying it by a Gaussian and calling it?
So this has very nice properties. It has nice properties when I want to Laplace transform the derivative of a function. If I want to Laplace transform the convolution of two functions. For a number of reasons we want to do this. It's much easier to compute. It works for almost all functions we would ever care about for real systems and dynamics and differential equations for control systems. It has very nice properties with derivatives and convolution that are inherited from the Fourier transform. And it's not clear that those would all be true if I used a different kernel, if I used a different e to the gamma t. Because a lot of what we're going to show because if I use e to the, when I say f of t equals e to the minus gamma t times little f of t, this e to the minus gamma t fits in really nicely to my Fourier transform, and I still get an exponential of my Laplace variable times time. And if I had this be some Gaussian, then it wouldn't be that simple. And everything would probably break, and I probably wouldn't have any of my nice properties, and this wouldn't work very well for solving differential equations. But you can try it. I've never tried it. I think it would be interesting. Might be the kind of thing I would put on an exam at some point in time. OK, I'm going to erase this. Any other questions about the Laplace transform? I think we should do some examples. Basically, the Laplace transform acts almost identically to a Fourier transform, except we can deal with a larger class of problems now. And so we can also deal with more ODEs and more PDEs than we could with a Fourier transform. And we're going to see that this is really a very, very powerful way of solving differential equations, is to take my equations, Laplace transform them, solve it in the Laplace domain, and then inverse Laplace transform, just like we did with Fourier transforms. But now we can deal with more functions that are, like we can deal with sines and cosines and exponentials and all the things we think we're going to be using. Okay? These are not my notes. Okay. So let's do a couple of examples, and then I'll give you a couple of properties, and then we'll end. Okay, so examples. So let's say that I have my function f of t, and I Laplace transform f, and I get f hat of s, s bar, or f bar of s. So I'm just going to do some examples. We're going to go down and see what some of these examples are. So what if my function f of t equals 1? How do I Laplace transform this? The Laplace transform is super, super simple. Like, it's easy to compute the Laplace transform. It's the integral 0 to infinity e to the minus st times my function, which is 1, dt. So what's the integral of this exponential with respect to time? Minus 1 over s e to the minus st. And I'm evaluating it at 0. I should just do this. So this is equal to minus 1 over s e to the minus st, evaluated from 0 to infinity. So e to the minus infinity, 0, right? So this equals 0 minus, so minus minus is plus, 1 over s e to the 0, and e to the 0 is 1. So this is 1 over s, just positive 1 over s. Everyone follow that? I integrated this, but since it's a definite integral, I actually have to plug in my values, and so that's where the minus becomes a plus. Okay, good. What about another example? What about f of t equals e to the at? Integral 0 to infinity, e to the a minus s t dt. That's the same as f of t times e to the minus st. Again, if I integrate this with respect to time, I get minus 1 over a minus s. But then I get a minus minus, and everything works out again, and this ends up being 1 over s minus a. These should look really familiar to a lot of you. And also, remember, we learned how to inverse Laplace transform this function in the complex analysis part. We did that horrible, nasty Bromwich integral over there to compute the inverse Fourier Laplace transform of this, and we ended up getting this function. Inverse Laplace transforms are generally super nasty, and we're not going to do much of that. Okay, but you know how in principle. Okay, other ones that are important. So f of t equals sine of some frequency times time, or equals cosine of some frequency times time. Then s hat would equal either a over s squared plus a squared, or it would be s over s squared plus a squared. So Laplace transform of cosine is s over s squared plus a squared. What about if my function was a polynomial t to the power n? I can Laplace transform this, no problem. To Laplace transform this, I assume you would just use the convolution property, and which I haven't told you yet, but I will soon. So f bar of s equals n factorial divided by s to the power n plus 1. So it's kind of like integrating a bunch. It's kind of like this 1 over s a bunch of times. You can also do this for Heaviside functions and for any other functions. You can find them in the notes. Just Google Laplace transform table, and you'll see, like 100 of these. And you should look at them and just make sure that you're familiar with a few of the most important ones. Okay, good. Easy to compute the Laplace transform. Fairly difficult to compute the inverse Laplace transform, but we have tricks, and we only have to do the hard step once, and we have lookup tables. Okay, so I wanted you to know how you would do it if you ever needed to, but in principle, we're just going to use lookup tables for inverse Laplace transforms, or MATLAB, or Mathematica, or whatever. Okay, the last thing that actually makes this useful is the fact that just like in the Fourier transform, if I took the Fourier transform of the derivative of my function, I ended up getting something much simpler in the frequency domain. That's also true of the Laplace transform, because it's basically a generalized Fourier transform. So I think that the reason this is called the Laplace transform, I don't actually think Laplace invented the Laplace transform, but Laplace was the first person to actually use the Laplace transform to solve ODEs and PDEs. And he was really thinking in the frequency domain, where you can do all of your math much more easily. He had that insight that you should be doing your math in the Laplace transform domain. So that's really why it's called Laplace transform. Okay, so important properties. And I'll probably just have time to write down 1 or 2 of these. So the derivative property is by far the most important. The derivative and the convolution, just like in Fourier transforms. So if f bar of s equals my Laplace transform of f of t, then I want to know what is the Laplace transform of df dt, of f dot. What's the Laplace transform of f dot? Okay, so let's actually plug this in. What's the Laplace transform formula? 0 to infinity, df dt, the function, e to the minus st, and we're integrating with respect to time to get rid of time to go to the frequency domain. Okay, just like in the Fourier transform, how do I solve this? Integration by parts. So I say this one is du, u dv, sorry, dv, and this one is u. And so if I want to integrate this by parts, I say, well, that's equal to u dv, sorry, uv, which is just f of t e to the minus st. So uv evaluated at 0 to infinity, minus the integral of v du, which is f of t, v. And then d, this with respect to time, is just minus s e to the minus st. And I'm going to pop my minus s out front because I'm integrating with respect to time. Okay, so this right-hand part is actually really simple now. It's just s times the Laplace transform of f. Before, when we did Fourier transforms, this term went to 0. Does anyone remember why? Because it was from minus infinity to infinity, and my function f was guaranteed to be 0. But that's not true here. This is a little bit interesting. So it is true in plus infinity. E to the minus st is going to be 0. And so this whole thing is 0 for plus infinity. But for 0, I get minus my function evaluated at time 0 times e to the 0 s, which is 1. So I get this extra term that comes out. I have a constant in addition, plus s times the Laplace transform of my original function. So it's very, very, very similar to doing the Fourier transform of a derivative, except it's a little different. Everything's a little different in a frequency domain. I have a constant term that I pick up. It's my function evaluated at time 0. But this term looks basically the same. Remember, s, if I plugged in I omega, this would be the Fourier transform of the derivative. All right, Fourier transform of the derivative is I omega Fourier f hat. Yeah?
You have a Heaviside function that occurs at f0. How do you evaluate the initial condition?
Great question. Yeah, I think you would say that this is 0 plus. Let's talk a little bit more about that later. That's a really good question. Okay, does the derivative make sense? I mean, we derived it. It's like integration by parts, pretty simple. And it's very, very similar to the Fourier transform, right? This term is identical to the Fourier transform if my function f was well behaved and s equaled I omega. Okay, you can also do this for higher derivatives, and you just get more and more terms. You can check it out in the notes. Just please look at it in the notes. You can do this for higher derivatives. And it's just integration by parts again and again and again, and it's easy, but it's also kind of horrible. You can do this for convolution. So if f bar equals the Laplace transform of f of t, and g bar equals the Laplace transform of g of t, then the Laplace transform of f convolution with g is equal to the Laplace transform of f times the Laplace transform of g. So this is, I can't overstate this. In the frequency domain, if I multiply two functions, that's like taking the convolution of those two functions in the time domain. Very, very important. Multiplication is a lot easier than doing a convolution integral, right? Pointwise multiplication for every frequency s, much easier than doing this nasty convolution integral. So this is a better representation for a lot of systems. If I have a convolution, I might want to Laplace transform it, and things become a lot simpler. So we're going to see why this is useful and why these two properties are useful. We're going to start solving ODEs and control systems on Wednesday. And then on Friday and Monday, we're going to get into PDEs. Okay? So think about this. Think about how this is the same as Fourier transform, and this is not a huge stretch. It's just a generalized Fourier transform. And on Wednesday, we're really going to see how much simpler problems are when we Laplace transform first. Okay, thank you.